I'd like to go over these properties of rational exponents. They're just as good as the original ones. We know that if we have a common base, a times a, I'm allowed to add their exponents. So the same thing goes here. If I have a common base of 5, I'm going to add the exponents. And 1/2 plus 3.5, or 3 over 2, 1.5, is 2. Okay? And then here is the only time I get to multiply exponents. So I multiply my exponents. And same thing happens here, and the 2 is going to cancel, and I'm going to get 5. Going on down here, you know that if I have the exponent on the outside, everything inside is going to get that exponent. And that's what happens over here. The 16 gets it, and so does the 9. They both get the exponent. The square root of 16 is, you say square root. Well, the 2's on the bottom. It goes out to be the index for the radical. So the square root of 16 is 4, and the square root of 9 is 3. And then I can say 12. Okay? Going on, you know that a negative exponent means put that thing under 1. If it's already under 1, then take it out and put it on top. Same thing happens here. I'm going to put it underneath 1. The square root of 36 is 6, so that's underneath 1. You know that if I have a common base on the bottom of a fraction, it means I'm dividing by that. And if I'm dividing by a to the n, I can just subtract. If I have a common base, I can subtract my exponents, top from the bottom from the top. Everything in subtraction is kind of backwards, right? So the bottom from the top. But you see what I mean there. So the bottom from the top. So here's the top, and I'm subtracting the bottom from it. 5 over 2 to subtract 1 over 2, I get 4 over 2, which is 2. 4 squared is 16. Everything inside gets that m, so the a on the top gets it, and the b on the bottom gets it. So if I'm taking the third root, that's what 1 over 3 means. I'm taking the third root. Remember, the number on the bottom is the index of the radical. So the third root of 27, well, that's 3. And the third root of 64, well, that's 4. Okay. You can see these exact same things happening in this example. And so let's go ahead and do it down here in our problem. And so we'll say, these are not a common base, so I cannot add those exponents. That seems like a trick. You want me to add these exponents? No, I'm not going to do it because the 5 and the 7 are not common bases, so it's a good exercise for that. However, the 3 affects everything, and this is the one time I get my chance to multiply exponents. The only time when you're outside of parentheses. This is it. So 5 to the 1/3 times 3 over 1. I'm just going to write it out. Times 7 with the 1 over 4 times 3 over 1. This is over 1, right? Yeah. So that's 5, because 5 to the 1. And 7 to the 3 over 4. Okay? And can I do anything else with that? Can I put these together? No, they're not the same. So I think I have to be content to say, well, I mean, I could with my calculator, because it's going to be 5 times the 4th root of 7 to the 3rd power. So sure, I can do that. Let me go ahead and do that on my calculator. 7 to the 3rd power is 343, and then I'm going to raise that to the 1/4 root, right? So I'm going to say 7 to the 3rd, and I'm raising it. I guess we already knew that. Let me write it the right way. 7 to the 3rd is 343, but I'm raising it to the 1/4 power because the 4 out in front goes underneath when it's a rational exponent. This right here is a rational exponent. It's a fractional exponent. And then I'm going to multiply the result by 5. So let's see. 1 over 4, I raise 3/4 to that, and I get 4.3 and some change, times 5 is equal to 21.52 all round. I'm sure, I have a feeling they didn't want me to go that far. This is where I would stop if I didn't want to pick up my calculator, but this is where I end up if I do. Okay, so over here, same thing happens, except, let me look at this for a second. That's the square root of 20, right? The square root of 20, we don't usually write the 2. We're looking for twins inside. And the 4 is 2 times 2, right? So I can take one of those out. So I could say 2 times the square root of 5. So instead of saying 20, I could say 2 times 5 to the 1/2, right? Over 5 to the 1/2. Oh, look, they're going to cancel. But everything's going to be affected by the 3. So 2 to the 3 and 5 to the 1/2 times 3 over 1 over 5 to the 1/2 times 3 over 1. Either way, this is going to cancel, right? If it's 5 to the 3 1/2, I'll still cancel it. And I'm going to get 2 times 2 times 2, which is 8. Okay? And I can certainly do that on my calculator if I want to confirm that. Is that rule really what just happened there? That's a really strange thing to be saying. And, I'm tempted to try to do this a different way just to make sure that you believe me. Let's see. If I said 4 times 5 to the 1/2, I could say 4 to the 1/2 times 5 to the 1/2, right? Because everything inside gets affected, right? And then I have 5 to the 1/2 on the bottom, right? So they're going to cancel, and then I have 4 to the 1/2, which is the square root of 4. And by the way, the whole time there was a 3 out there. I don't mean to forget that. It's going to end up being 8 no matter what I do. I'm not sure if you're pleased with that, or if you're sitting there saying, But take the square root of 20, all right? That's what this means right here, the square root of 20, okay? And then say the square root of 5, okay? So the square root of 5. And now divide the square root of 20 by the square root of 5. And I got 2, okay? And then I raise it to the 3rd power in my calculator, and it is indeed 8. So if that seems squirrely, you can always check it on your calculator. It's not like you can't.